in a lecture with Professor Stein from Princeton. It would take me at least a 15-minute lecture to just touch on some of his accomplishments, and then John will certainly kill me. So, for my own sake, let me just mention that Professor Stein has received the National Medal of Science, the World Prize, a couple of Steele Prizes, and mathematically, by descent, he's Polish.
Thank you very much. It's a great pleasure to be here. So let me begin by a little confession. When I was first thinking about this lecture, I thought I would talk about two recent results that I've been interested in singular integrals, which are related to subatomic variables. But then when I started to prepare it, I realized I wouldn't have time for two, so I'm only going to limit myself to one. So the new in this title is much reduced. So what both of these results were sort of related in the sense that they both require different variations of what's called the Calderon-Zygmunt paradigm. So I want to concentrate just a little bit on that and start by a little bit of reviewing. So, I'm going the wrong direction. So I'm going to divide the lecture into three parts. First, a quick review of some classical singular integrals, and the second part is already quite a transformation on the point of view, which involved the theory of the Cauchy integral in the plane. And then I come to the third part, which is joint work with Loredana Lanzani, trying to develop a sort of corresponding theory in n-convex variables, but it looks quite different in many respects. All right, so let's go to that. So very quickly, Christina gave you an introduction. I'm going to give you a slightly different introduction to singular integrals in Rn. They're convolution operators. And this is just one possible way of talking about singular integrals. Everybody has a different definition. So they're convolution operators with kernels, which are distributions, but these distributions are equal to functions away from the origin, and they satisfy certain differential inequalities, and I'm taking the most extreme case where they're as smooth as possible away from the origin, and they satisfy characteristic kind of differential inequality. But in order to be thought of as distributions, they also have to satisfy cancellation properties, and there are a variety of equivalent ways of stating these cancellation properties. Maybe the nicest way is to start with a fixed bump function, that's a C-infinity function, supported in the unit ball, and then we take the dilates of that bump function, and then we test that distribution, and that test should be uniformly bounded. That's one way of stating the cancellation properties. So there are many examples of this. One is the first example in one dimension where the function is 1 over x, and the distribution is the principal value associated to 1 over x, and up to a factor of pi. That's the Hilbert transform, of course. And another one is the kind of first by Miklin and Calderon-Zygmunt, where n dimensions are homogeneous kernels of the critical degree, and they're smooth away from the origin, and they satisfy, in that case, the cancellation condition is stated that the integral of the kernel on the unit sphere is equal to 0. All right, so those are, and of course the basic theorem that I want to focus on is the theorem that these operators are bounded on LP, which of course goes back to the one-dimensional case by Marcel Rees. Oops, I'm going in the wrong direction. So now just a very important variant of this are the classical pseudo-differential operators. And they're operators which are given in terms of symbol and Fourier transform. And here the symbol satisfies differential inequalities, which are somewhat reminiscent of the differential inequalities that the kernel satisfied, and we write these operators. And this class of pseudo-differential operators is the class that arises if you take the singular integral operators that were on the previous transparent slide, and you mix them, cook them up with the simple operations of multiplication by smooth functions, and you also restrict everything to kernels which have compact, essentially have compact support, because you want to localize everything. And then you're going to get something of this form, and these operators are again bounded on LP between 1 and infinity, but they form an algebra, and what's very important for the application, but I'm not going to pursue this, is that this algebra is nearly commutative. In fact, that you can read off in terms of the symbol what the product of two operators are. The product is essentially the operator whose symbol is the pointwise product of the symbols plus an error. And the error is measured in terms of smoothing operators, which I'm not going to get into, but you have to think of those operators as small errors. Now, very quickly, let me mention now, come to the Calderon-Ziemann paradigm for proving LP estimates, and it goes in two stages. First, one proves the L2, one does the L2 theory, and then one does the LP theory first via a weak L1 argument. And very quickly, in this case, the L2 theory is very simple in the first transparency, where it was given by a convolution operator. So all you have to do is to prove that the Fourier transform of the distribution is a bounded function, because on the Fourier transform side, this operator is nothing but multiplication of the Fourier transform by this Fourier transform of K. And so that works very simply, because informally the Fourier transform is just the integral against the exponential, and you break up the integral into two parts, one where x is less than 1 over the norm of c, and one where x is bigger than 1 norm of c, but you break it up smoothly, so you break it up with a smooth bump function here, put that in here, and you put the rest in there. Now, if you put that in here against e to the minus 2 pi I x c, you see that this is exactly a dilated bump function, this product. And so this integral, which is the distribution really tested against this dilated bump function, is uniformly bounded. That proves the boundedness of this. And the boundedness of that, here's where we use the differential inequalities, and we take advantage of the oscillation of the exponential just by integrating by parts a number of times. And each time we integrate by parts, we differentiate the kernel, and it gets better and better, just the right rate way at infinity, and that's it. It all works out very nice. Now, the second part, we'll go over even more quickly, is the weak type 1-1 argument, and it follows. What's basic here is an analysis which involves the kernel, and in fact that the kernel satisfies such an inequality, which is itself a very simple consequence of the differential inequalities of the kernels. So those are the two ingredients of this method, very briefly. So now let's go on now to the Cauchy integral in one variable. So here is the Cauchy integral, and we're integrating over a curve. Now, the question is, first of all, if the curve is smooth, we are back essentially to the theory that was just described. For example, if the curve is the circle, and you write down for an arbitrary function on the boundary of the circle, you write down this Cauchy integral, you get, of course, automatically a holomorphic function in the interior of the disk, and if you pass the limit, you will get the periodic version of the Hilbert transform plus the identity operator But so that the behavior of this Cauchy integral is just the periodic version of the Hilbert transform. And if you do it in the upper half plane, you get exactly the Hilbert transform, except for the factors of pi and the identity coming in there. But so that's the case. Now, if you do it for a smooth curve, and smooth here means anything a little better than 1 degree of differentiability, then you can do either of two things. Either you can redo the theory more or less as it is, or you can approximate the Cauchy integral on the curve by the right kind of approximation back to the Hilbert transform. And so it's all reducible, and that approximation has a controllable error just because you're in the case of having 1 plus epsilon degree. Epsilon has to be a positive number. 1 plus epsilon degree of smoothness. So for many years, the interesting problem was, what happens if you don't have this epsilon? If you only have that the curve is C1, or more generally, which is sort of the natural context, if the curve is Lipschitz, which instead of having 1 continuous derivative, has 1 bounded derivative. And that led to very important developments. I mentioned Calderon, and then who did the case when the Lipschitz constant was small, and then Kottmann, McIntosh on there, did the general case. And then you might even do something even more general, ask for any curve, whether it's Lipschitz or not, and then this problem was solved by Guy David in terms of Al-force regularity, which still involves 1 degree of differentiability, but it also involves the geometric notion of the curve. So I'm not going to get into that, but what I do want to mention are developments that took place because of this side-by-side, which in some sense gave some of the essence of the ideas, and that's the so-called T of 1 theorem of David and Journet, and the version of it, which is the more general version called the T of B theorem. And so here is a theorem again about singular integrals, but now they're no longer going to be of convolution type, and the crucial thing is to do the L2 theory at this stage. And so the kernels look like that. The kernels still have their singularity on the diagonal, but they're not functions of x minus y, but they behave somewhat as if they were functions of x minus y. So they satisfy these differential inequalities. We only need derivatives of most degree 1. And now the cancellation conditions are stated in 2 ways. What happens, so I'm stating here a very nice special case of the T1 theorem, then I'll say what the general thing is. That the cancellation condition is that you take T of 1 and define it in an appropriate way, and it's 0. And a cancellation condition which is, again, for the bump functions of radius 1 over r, but now no longer necessarily centered at the origin, but centered at any point, because this is not translation invariant operator. And their L2 norm has to be what you would expect it to be if the operator was bounded on L2. And you ought to assume also that this condition, these assumptions hold not only for T, but its formal adjoint, that is for the operator which you would obtain when you interchange x and y. And so the basic theorem that they proved was that the theorem that these operators are bounded on L2, and the second part of the Calderon-Zygmunt paradigm were almost exactly the same. So that did not have to be reproved. So that was sort of the key point, and this is what I want to emphasize. Now, this is the special case, the simplest case of the T of 1 theorem. The general form of the T of 1 theorem is really the one that occurs in many applications, many other applications, and that's not to assume that T of 1 is 0, but to assume that T of 1 is BMO, and also that T star of 1 is BMO. Now, in order to prove this theorem, there are two parts. To prove this simple case, all you need is some almost orthogonality decomposition, and to prove the second part, you also need the notion of paraproducts. All right, so let me just say a few words about the Cauchy integral about the Cauchy integral for a Lipschitz curve. So a Lipschitz function is a function which satisfies this kind of inequality. So the Cauchy integral for a Lipschitz curve can be thought as an integral over the reals with k of xy being given by exactly this function. Now you notice this term 1 plus I a prime of y, that comes from the d zeta in the Cauchy integral representing the curve. And so there is this version of it, or there is the version when you get rid of this factor, and then you try to put that factor in the function. So these are different versions, but they each have their strengths and their weaknesses. So you see this version has no smoothness in both variables, because whatever smoothness we had, which was the Lipschitz condition, is now we have a prime and we just have an L infinity function. So we cannot use the T of 1 theorem for this thing. On the other hand, we'd like to use it for this. It would be good enough to use it for this kernel. But then we lose the nice cancellation condition. Of course, ultimately they will be proved, but then we lose the ability to give a simple proof for the cancellation condition. So this is a problem that has to be faced. So if you're going to prove the Cauchy theorem this way, you have to generalize the T of 1 theorem further and call it the T of B theorem, etc. I don't go into this because now I finally I just want to give you a feeling for what it was. All right. So now we come to the Cauchy integral in CM. Now, for a long time, I thought to myself that one should be able to do a theorem in n complex variables, which in some sense inherits the theorem in one complex variable. It's a generalization of this. So the idea would be to write some Cauchy integral on a domain and have the minimal smoothness on the domain, and then prove the L2 theorem and maybe the LP theorem for that Cauchy integral. All right. Now, this seemed very difficult, but it turned out in the end not to be so difficult. So I'm going to describe what are the results that Lanzani and I have obtained. They're still not written up in final form, but I think vouch for them. It takes forever to write anything down. It takes longer and longer, it seems. Anyway, so here are the main problems in looking at such a thing that one is faced. First of all, there is no unique natural Cauchy integral when you get to CM. We're going to see right away that there are Cauchy integrals, but there's no one issue. You don't have a 1 over z minus zeta, which you integrate in some sense. That's it. All right, so there's a choice to be made. Secondly, here's another thing that you don't see at all in one complex variable. So pseudo-convexity has to play a role of the domain. That's just experience, everything in several complex variables. You can't just think of things happening on domains, even if they have smooth boundaries. Pseudo-convexity is the play role. Now, if pseudo-convexity, if you buy this thing, maybe I can sell you the book and put it, but if you buy this thing that pseudo-convexity has to play a role, pseudo-convexity is a notion which involves two derivatives. So therefore, this means that our best expected results should be not near C1, like we have in one complex variable, but near C2. All right? That's background. Now, let's come to the next issue, which is what do we want, or when we say we want to have a Cauchy integral and prove a theorem for it, what will a Cauchy integral be? So it'll be some kind of integral where you have the domain omega in the complex plane, which has some minimal regularity property, and you start with a sort of a general function on the boundary. W's go to the boundary, and you integrate it, let's say with respect to the induced measure, the induced Lebesgue measure. The domain is smooth enough to carry the Lebesgue measure, and you, for Z inside the domain, you have a new thing. And what you want is for this object, first of all, that this kernel should be given by some natural or explicit, should be attached to the domain at least in some non-arbitrary way. Okay, first of all. Second of all, you want it to automatically reproduce holomorphic functions. That is, if f arose as the boundary value of a holomorphic function, reasonable holomorphic function, then this Cauchy integral should give you back f for every interior value. And secondly, no matter what f was, whether it was boundary value of the holomorphic function, they should automatically always give you a holomorphic function. Of course, that's the property of the Cauchy integral in one complex group. So those are the, now I'm going to tell you that there are a series of definitions which certainly give A and B. And there are many such operators, but C is much more problematic. But so let me very quickly tell you what many of you probably know about this. These are the so-called Cauchy Fantapié integrals or kernels. And there's a long history, which I don't really know very well, but here are some of the names and the dates. So Fantapié, Leray, Koppelman, and many others have worked out this very beautiful formalism, very unexpected formalism, which reduces down to the ordinary Cauchy integral. So what is this? And this formalism will automatically give us A and B, but not C. So A and B are those two, they will not give us necessarily C. That's much more problematic, as I said. So, in order to, what we start with is any vector, n vector, we're in Cn, of functions which can depend both on W and on Z. W is on the boundary, Z is in the interior, and from which we automatically also think of it as a one form, write it this way sometimes, thinking of it as a one form. And then we take the inner product of this with the vector Z minus W. That's, of course, an n vector. We're in Cn. And that's the inner product without complex conjugates. It's real dual. Okay, and what you do is you take this delta, this basic, that's going to be the basic denominator, and you assume that that denominator, when W is on the boundary and Z is in the interior, is nowhere vanishing. And you put that in here, and here this G is a one form in the W, and now you take the D bar of G, that gives you a 1, 1, 2 form, and you wedge it with itself n minus 1 times, and then you wedge it back with G, which is a 1 form, and then you get, you are in Cn, so you have dimension 2n, and here you get a form of degree 2n minus 1, and so you can integrate this on a boundary. And so you integrate this with the function on the boundary, and that is our candidate. That's what is the Cauchy Fantapié, etc. integral, and it has the properties A and B that I mentioned. First of all, it is naturally attached in some sense. Once you've chosen these G's, of which there are infinitely many choices if you're clever enough to make this thing happen, but it does reproduce automatically holomorphic functions. Now, in order to achieve C, this becomes quite interesting. It was observed or proved, I don't know how to phrase it, by Leray already a long time ago, that in the special case, when the domain is strictly convex, we don't know what that means, and smooth. It's not, I think, interested in minimal smoothness. Then, if you take for G just the d rho, the d of rho, that's from rho is a defining function. We take rho to be a defining function. I didn't say what. Yeah, rho is a defining function for omega. It's a function which is 0 when exactly on the boundary of omega and its gradient is different from 0. If you take a defining function and you take d rho, d with respect to the w variables, you get the desired 1 form. And notice that in that case, this denominator, this crucial denominator, is now a linear function in Z. So it's holomorphic in Z. And so it's non-vanishing. That's what follows from this convexity. And so you get everything that you want for a Cauchy kernel in that case. Now, there's another case that was studied much later, and it was studied by Henk and Ramirez and Holt, who has very important development that took place. In the case when you have strict pseudo-convexity, how much time do I have left? 20 more minutes? 20 minutes, okay. They showed that you could make a variant of this, involved quite a construction, which the domain is smooth, for which you can do, again, obtain something which is analytic in Z, which is what you want. All right, now, very quickly, there are certain notions of convexity that I want to mention. There's the notion of strict convexity, which means that if you take the defining function and you take the Hessian, the tangential part of the Hessian, it's a strictly positive definite matrix. Okay, then there is another notion, the notion we're going to use, which is more general than that, which is called strong C linear convexity. I'm sorry for the very complicated terminology, but I think that exists somewhere, and so we're following that terminology, which means that this quadratic form limited to the complex part of the tangent space. You see, the tangent space, which is of dimension 2n minus 1, has a subspace of dimension 2n minus 2, which is complex in the sense that it is invariant under the application of J, or multiplication by I. And just restricting it to that subspace, this quadratic form is positive definite. And then there's still a more general notion, which is what's called the usual strong pseudo-convexity, which is if you take this corresponding Hermitian form. All right, so those are the notions that play some role. So now, this strong C linear convexity that I just mentioned has a very nice geometric interpretation when the domain has a smooth boundary. It means you take any point on the boundary W, you look at the tangent plane at that point, and then you now just look at what I call the complex part of the tangent plane, and you look at any point Z in the interior, and then this inequality has to happen. The distance of Z from this part of the tangent plane has to be greater than the distance of Z from W squared. Okay, so that is the notion of, that's a notion of strong. And now, to note the class of smoothness, which will involve 2 degrees of smoothness that we want, is what's called C11, which means the function is of class C11 if the first derivatives are Lipschitz. Okay, and so a domain is of class C11 if it has a defining function which is of class C11. And now we will say that for those domains which are not smooth, we will say they're strongly C-linearly convex if they satisfy the same geometric inequality. So the theorem is that assume that omega is of the above kind, and now if we take the Cauchy from Papier in the Loré special case, then that is a bounded operator to L on L2. And the addendum is how to state that precisely. You start with a C1 function on the boundary, and then the Cauchy-Loré transform gives you an analytic function in the interior, which continues continuously to the boundary, and now you consider the operator which maps functions on the boundary to functions on the boundary, the resulting operator. It extends to a bounded operator on L2 and also on LP. And now, that is the theorem. Now let me just say something about the proof of that theorem. Oh, before that I want to say that if you strengthen that assumption slightly from C11 just to C2, then there is an analog which holds for the strongly pseudo-convex case. And that is sort of satisfying from the point of view of how one thinks about the subject. Strongly pseudo-convex is sort of a natural thing. But then you have to modify this Loré transform so that it makes good sense. Now, let me just make some remarks. The first set of remarks is that there are a series of examples developed by Barrett and Lanzani. I don't know whether they're published yet, but they're for Reinhardt domains. So they have circles in them, and there's Fourier analysis in the circle, and you can read off L2 results much more easily. And these show that you cannot really change much the assumptions. That if you only assume C2 minus epsilon, things would go wrong. And even if you assume C infinity, but don't assume the strict convexes or strict pseudo-convexity, things may also go wrong. So we are right at the edge of what's best possible. Now I want to mention two things which we do not see in the situation of one complex variables, but which are sort of minor miracles. And when we found these things, I was very pleased. Anyway, first there's a very important sort of technical problem. It's a little more than technical problem. We will see that we're dealing with functions which are of the class C11, and our integrals will involve integrating various combinations of second derivatives of these functions, not on the whole space, but on the boundary. Oh. What? Well, so the only thing I can say is I've brought a set of transparencies which can cover the same thing.
Overheat.
There probably needs a fan. Somebody bang on the
I wasn't prepared for this. I just didn't know which method was considered best. So let's see.
push it forward. It's too far back. Turn off the
Is it
lights.
possible to push the projector further back? That looks good. No. Or maybe you move it on closer.
Is there an engineer?
You can tilt the mirror. Now, is it focused? All right, anyway, so the theorem where I want to say it's good. That's as good as it goes. Is here is a Cauchy integral. Just quickly reminding you what it is. It's rho is of class C11. Omega is strongly cylinearly convex, and then the theorem is that it's bounded on L2. That's the main theorem, because then proving the LP inequality from the L2 will be easy. Now, just a few things about C11 that I've said before. Here is on this domain, we're in Rn, which is C, and N is, capital N is 2N, and that's a definition of Lipschitz function. That's a definition of the C11 function. And okay, I think I've said all of these things. And the induced measure, if we look at a coordinate chart, we can write it as a graph in a lower coordinate chart where the function phi is still of class C11, but of one less variable. Okay, and this is the induced measure. The induced measure is then equivalent to the Lebesgue measure. All right? So now let's come to one of the main questions. Here is the question I want to rephrase. So for example, let me first ask it on a Lipschitz function. Suppose you have a Lipschitz function on R2n. Can we define the first derivatives of this Lipschitz function on the boundary? Or if you have a function which is of class C11, can we define the second derivatives on the boundary? Because the boundaries are lower dimensional things, set of measure 0. And the answer is, of course, no. So what is going to save us? What is going to save us is that in some sense, the only thing we are involved with are second derivatives which are in some sense tangential. And then there is a good theory for the first derivatives, in this case, or the second derivative. So here's another version of the problem. We're going to integrate forms, and so we have here a omega is some kind of a test of which you can think of as being a form of a complementary dimension which is continuous. We want to be able to integrate df if f is Lipschitz on the boundary. Or what we really want to integrate is d bar df if f is of the class C11. Can we do that for, and the answer is yes, and we can do this and also do the right approximation. Now we're going to have to do not only this integration, but we also somewhere have to do another integration by parts, which will involve putting a third derivative on our function formally, which we can't do. And so we can only do this if we have functions which are very smooth, but we can approximate by smooth functions. So here's the statement of a lemma, of a key lemma, which is that if, for example, if we let J be the inclusion mapping of the boundary into R2n, and J star be the pullback mapping, which takes the forms on Cn, which is R2n, back to the boundary. Now the approximation lemma, let's say for Lipschitz functions, is that given a Lipschitz function in the whole space, there's a sequence of C infinity functions, f sub k, such that the f sub k converge uniformly on the boundary, but the gradients are uniformly bounded, and so that if you take J star of df, this dfk, they says, and of course you're restricting now to the boundary, they converge pointwise almost everywhere. The coefficients converge point, and of course boundedly almost everywhere with respect to the boundary measure. And similarly, when you're in the C11 case. So that is one of the main lemmas that has to be proved, and there is a version of this which involves the Hessian of a function which is of class C11, but restricted to the boundary. And I just want to state it very quickly. So that it states that if you have a C11 function, you would like to have this kind of expression with a term little o of h squared as h tends to 0, when h are restricted to tangent vectors at the point W. that would be the quadratic extension, the Hessian, if you had smooth function, which had a continuous second derivative. And the point is that there is such an expansion about the point W for small h, when h is in the tangent space, for almost every W, if you start with a C1 function. All right, and this has various consequences. I'm not going to. All right. Now, then there's another very nice thing that surprisingly enters here. There is a very natural measure on the boundary, which is equivalent to Lebesgue measure, but that's the measure we want to use. And it's somewhat akin to the struggle which one had in the C1 case when I said that 1 plus I times A prime, there's a two-way, but here it's a real thing. So this measure comes about when you look at the Cauchy kernel, and it also involves the Levy kernel. So we could call it the Levy-Leray measure. Okay, now suppose we have a domain omega, which is C11 and strongly C-linearly convex. Actually, at this stage, you don't really need C-linearly convex. You strongly convex, if you could define, strongly pseudo-convex, if you could define that notion for C11, would be all right. So here is the measure. You just integrate the numerator of this Cauchy-Leray integral. Remember, there was a denominator which had singularities, but you integrate this numerator and you find that that thing is the determinant of the Hessian restricted to the complex tangential part, the determinant of that multiplied by the gradient up to a constant times d sigma. And so our Cauchy-Leray integral is just very simple. With respect to this measure, is just to integrate the function times this basic denominator raised to the nth power. By the way, I should have noticed that when n is equal to 1, you get, of course, the usual Cauchy, everything cancels out. But everything just cancels out. So that's what, and now we can, it's natural to prove the boundedness in L2 for this operator. You could, of course, introduce an equivalent measure, and it would be the same L2 boundedness, but you couldn't prove it because it would have a part which would have no smoothness. So that's the operator that we're going to use. And now, the second accident, which I have meant. Now let's see, am I out of time?
You're fine.
I think now in this confusion of whether to go from here to the transparency, I think I left out an important point. Now we're coming to this other very important difference between the case of this sort of minor miracle that happens when you, for n bigger than 1, the thing about the Cauchy kernel is that the Cauchy kernel in some sense is a derivative of something which is good. Now in one complex variable, Cauchy kernel is 1 over z or 1 over x. And if you think of it as a derivative, it's the derivative of log. And log is bad because log has lost the nice homogeneity. While in the Cauchy kernel in higher dimension, it is the derivative of something which has 1 less homogeneity, but it still has the right homogeneity. And that allows you to do the cancellation because it allows you to put the derivative by some integration by parts on your bump functions, which is how you measure the thing. So let's come to that point here. So I think, what does it say here? Maybe, so I have this thing. Now I think I'm really confused about which transparency. Aside for a minute. All right. Now, I want to say that all we need to prove in applying the T, an analog of the T of one in this setup, is the cancellation properties for this operator. Because this operator, with its kernel looking like this, still inherits 1 degree of smoothness. Because you remember the delta was done in terms of, involved just the d rho. And rho had 2 degrees of smoothness, so the denominator just involved d rho. It has 1 degree of smoothness, so it satisfies the differential inequalities that are necessary to apply the analog of the T of one theorem. If we have the right notion of space of homogeneous type. And so very quickly, let me show you that there is a natural notion of a space of homogeneous type, which comes from this denominator. Taking the square root of the denominator gives us a natural notion of distance between 2 points, and the distances are locally in coordinates, just look like the distance on the Heisenberg group at each point, and they satisfy the inequalities of the distance, and they satisfy first derivative properties. The kernel satisfies first derivative properties. And so all the machinery that is used to prove the LP result from the L2 result is present, with not much change. So everything reduces to proving the cancellation properties that are needed. And now let me just finish by showing you that part. So I'm going over lots of things very quickly, and hopefully this will make sense. So I'm saying that the extension of the T of one theorem to spaces of homogeneous type, this extension is not such a difficult, a little complicated thing, but that was also carried out by Rene and Stein. We can apply it to our Cauchy integral if we can do the cancellation property. And now I'm talking about this little miracle, which is the integration by parts. So I'm writing down another integral that looks like the Cauchy integral, except it now has the denominator taken to the power n minus 1. So it is not a singular. In fact, on very crude basis, you can see that it takes continuous functions to continuous functions. In fact, it takes continuous functions to smooth functions. But what happens is that the Cauchy-Loré integral of f is this more smoothed out version of d of f. That's the integration of magical integration by parts, but it's not exact. But there is an error term that holds for. Error term means it's a term which is automatically smooth, and so it's easy to take care of that. And there's a similar identity for the formal adjunct, and that would prove the properties that would be needed to apply the L2 arguments. Now, the last transparency I want to show you is how does this integration by parts work. And you see here the problem is we are right on the edge here because we have our rho, which is a class C11, and we have 2 derivatives. So this is a function which is only defined by this limiting process and is defined almost everywhere on the boundary. And now we're going to do some integration by parts, which would have to hit this thing, which of course it can't. But so the idea is, well, let's try to do this integration by parts. So S of df is this way, and now the integration by parts, sorry, let me make it more visible, puts the d on this side with a minus sign. Okay, that doesn't change anything. Now the d can either hit this or it can hit this. Now if it hits this, it does just the right thing. It basically transforms the 1 over delta to the power n minus 1 up to the factor to 1 over delta to the power n, which is what we want. But it also hits that. But it hits that and it's 0 if was legitimate to say that, because then it's a D of a D, of some D, and therefore it's automatically 0. So how do we do this? Well, we do this by doing this identity not for F, but and not for rho, but for the approximation of rho, which are given by that lemma, and then everything works out. And that is the long and short of it. I think with that, stop.
Thank you very much. Are there any questions or comments?
So you said
Yes.
you said something that I can't quite capture again about the strongly pseudo-convex case
Yes.
of this.
So the strong pseudo-convex case, you cannot write down the same integral, because that same, if you wrote down the analog of the same integral, you would have something good for z close to w, but for z away from w, things may go bad, and you may have, you may have vanishing where you don't. So that's why in the Henkin and Ramirez and those guys do various corrections, either by d bar or something. There is a correction that you can make of a different kind that Kurtzman and I did in the smooth case many years ago, and you can adopt it in this case without too much difficulty, and therefore you can also do the C2 case. But that correction requires strong pseudo-convexity. I mean, that correction requires C2-ness. It requires that that the second derivatives be continuous, because you're making corrections in little neighborhoods where you're close to some fixed thing, and you're freezing that, and you cover it by little neighborhoods. So, in other words, the more general geometric situation, strong pseudo-convexity requires you pay with it. Now, whether this is the ultimate, it's a little hard to say, because it's in part a question of which operator do you formulate to have the theorem, since there is no God-given Cauchy integral. So all I can hope to convince you is that these are reasonable versions under the circumstances of Cauchy integrals, and these are reasonable conclusions.
You were going to say something about the new?
Well, that was one of the new things. What? Well, I was also going to say that, I'm sorry, it takes a whole lecture to try to explain that. But there are other problems which involve where you cannot use the LP part of the construction at all to prove the LP boundedness. And there you have to use some square functions, Littlewood Paley, to prove LP, which is the only way of doing it. Because the kernels no longer have sort of local singularities on the diagonal. And so they don't allow, they're no longer going to be weak type on life. So that machinery doesn't work. They look a little bit like product kernels. I was going to say something about that. That's also interesting. And if I started to talk about that, this would also. Nobody asked me, how did I know that this was That'd be great.
Well, thank you very much.